Hey guys, what's up? Eddie Aho here with KissAnalog.com. Today, what I want to do is talk about common mode chokes. They're found in just about every EMI filter. It's a way to filter out the common mode noise. Thus, common mode choke. So what I'll do is I'll bring you over here and I'm going to show you in this filter, in this power supply here, where the common mode choke is, kind of what it looks like. And there's actually, they look different. I mean, they come in different varieties. One of them is on a toroid, like on a core like this, okay? Now, there's special cores for common mode chokes for EMI filters. You use a different core than you would for, say, a differential choke, or just an inductor that you might use for filtering would be more referred to as a differential or normal mode choke, where, you know, it's kind of the opposite of the common mode choke, okay? So here, let me show you something. Got my board here, and so sometimes it's referred to as a CM for common mode, okay? A CM choke. And it can have different symbols on your schematic. A couple common ones are this one, where you see each coil has a dot, and it has these little bars here show that it's on the core. Yeah, so this represents a common mode choke, and this does too. Now this one might just be called a Zorro, okay, with just a Z like this, showing that these two guys are coupled together as a common mode choke. And so it's just understood that it's hooked up like this. And the reason why that's important is the differential current, right? The difference between these two lines, the input voltage, that's the difference, and the difference over here. So the differential current that's applied to this circuit by having a voltage here, the current would flow through here, go through your circuit, come back and out this way, right? So that's your differential current flow. When that happens, the current flows through this dot. This wants to build a field on that core. Then the current flows through your circuit, comes back this way, and it's going to the non-dot end. So this is going to make a field on that core, that same core, in the opposite polarity as this one. So they cancel, okay? And that's the idea. So in a common mode choke, ideally, it's pretty much zero impedance to differential current. It's not, but I'm just saying that ideally it would be, okay? Because they would completely cancel. But they don't, and that's what we call leakage inductance. One of the names for it, okay? Now, so how does it work then? So common, if you have some noise here and some noise here, they're the same phase and amplitude. They're coming in here into your circuit. They both hit the dot. They both build a field, and so you're getting a huge field built, and it chokes. It chokes it off. And then you would have Y caps from here to chassis ground, and from here to chassis ground, okay? You might have Y caps over here to chassis ground as well, but that's your common mode. It's what's common to, say, chassis ground, that if you put a scope probe between chassis ground and say if this is neutral, right here, you would see the same voltage, same signal as if you put the probe from, say, line to chassis ground. If you see that same signal on both lines, that's common mode noise. And as it comes in your circuit, it's going to build that field and leak through the Y caps, okay? Now, if your circuit, you know, is generating common mode noise, which switching power supplies will, same thing this way. As they come this way, they're both going into the non-dot, and so it chokes it, right? So you'd have the Y caps here, and then that noise would go down to chassis. So that's how common mode choke works, and these are kind of the symbols of it, and sometimes referred to as CM choke. Now, if you just had one, you know, inductor on your line, that'd be differential, right? Because it's differential current. It's not seen by both of them. So if you just had one choke on your line, not this one, that'd be differential. So you say differential mode, or sometimes normal mode. So normal mode, okay? But we're talking about common mode chokes here. We're going to come over here and we're going to build one, okay? I'm going to show you what they look like. So let's come over here and do that. Alright guys, so this is a power supply we're going to look at, alright? And this is the input terminals right here. Danger, high voltage. So your input voltage comes in here, and of course that's an EMI filter. And once you've seen them, you start to recognize them. And then our bridge rectifier, our bulk capacitor, and then the rest of the power supply. Okay, so this is the input circuit to give our bulk voltage right here, our DC voltage right here. So we have to go through our EMI filter, right? So let's look at this. We're going to see what these pins do. As I flipped over this pin over here on this side here, comes down and connects to these two pads. And that's this side of the fuse. So the fuse comes over, and so come down here, jumps over the fuse, comes over here. So this is, say, the line voltage coming in here, the current, and it comes over here, and then goes through this circuit. And then there's a break right here. Now break would be this inductor. So this is not the common mode choke. This is a differential mode. This is a single winding, just two pins on it. So the current comes this way, goes through the choke, and then gets to this break. And then there's another break. And that's this common mode choke. Okay? So it comes here, it goes through the winding, comes out here. Then comes up to the diodes right here. See, here's the diodes right here. Okay? So that's how the line gets up there. The neutral comes straight in, straight shot, boom, boom, boom. No differential mode. Just comes through right to the common mode, hits this one, and then it looks like it disappears. So let's come over here. And you can kind of see it there, right? There's a little trace right under here. And it comes up here and over here. So maybe you can see that now. Comes around in that capacitor. Alright, so let's identify all the parts. We have an X cap. These are actually X2 caps, safety caps. I have a video on X caps, Y caps. I'll link it below. But this X2 cap, it's across the lines. Right here, these two pins. Then we go through our differential mode choke. And there's another X2 cap right here. Then we go through our common mode choke, and there's another X2 cap right here. But look, there's also a resistor down here. Let's see where that's tied. So it's tied right here to right here. So it's right in parallel with that X2 cap. Okay, it's on this side of the differential mode. Then the differential comes to this X2. So this guy and this guy are in parallel. So let's go ahead and draw that. And then we have our Y caps here. Let's jump over and look at our Y caps. Okay. Now, ground comes down here to these two pads. And then look, one of the Y2 caps right here goes to this. And then the other one goes to this guy. So, right here off the rectifiers, we have our Y caps. Okay. So the rectifier comes over here. Right to this one, to that Y cap, and up here to this one, to that Y cap. And then our common mode choke right here, okay? So then our common mode choke's right here. So the Y caps are on the rectifier side of the common mode choke. Alright, so let's just draw this circuit here. We come in and we go through that fuse, right? So we go through the fuse first. And then we come and we hit an X cap. So I'll just draw that here. I'll draw the neutral coming in right here. This is our line and our neutral. Okay. So we hit that X cap, but then we have that resistor. So we come over here. Whoops, sorry. That's supposed to be resistor. That's pretty terrible resistor. Sorry about that. This pen, the ballpoint kind of sticks on it. Yeah, I'm using excuses, I guess, here. But anyway, so there's our resistor, okay? RC, okay? And then we have this differential mode choke. So let's draw that. Okay? And it's differential. It's not on both lines, right? The other one just went straight across. And then we hit this yellow cap, this X cap right here. And I could read the values right on top. They say 0.1 mics. So, okay, there's another one. So all these are the same value. And then we have our common mode choke finally. Okay, so I'll just draw it this way. Yeah, this ballpoint feels kind of funny. And then there's another X cap. All right, and I'll just draw the Zorro symbol. Okay, I'm gonna also put the dots up here just for fun. All right, and then we have our Y caps and our bridge rectifier. Okay, so I'm just gonna show one more Y cap here. And it is tied to chassis ground, earth ground, right? It's gonna be earth ground. But first, as far as we know, it goes to chassis. Okay, and then it goes to our bridge rectifier. I'll just draw that like this. And that's our bridge rectifier, okay? Just draw a symbol like that. So that just represents a bridge rectifier, okay? And then we go off to our bulk capacitor. So that's basically the circuit, and these caps here are 0.1 mics. All right, and then I have to look at the value of those guys. All right, guys, very common value for Y capacitors, 4700 picofarad. Now the reason why that's common value, when you add those together, that gives you, if you do X of C, right? And that's equal to 1 over 2 pi FC. When you add two of the 4700 picofarads together and you come up with this X of C, and you put, say, 120 volts coming in. So 120 volts divided by your X of C, that's your current, right? That's leakage current. So 120 volts divided by that leakage current will give you less than half a milliamp of leakage current. So that's why that's common value. All right, so what is the value of these things? I've got my LCR meter. Here, let me just flip it over. Okay, we're going to measure this guy first. It's right here, those two pads, right? So this is in circuit, so maybe not 100% accurate, but pretty close. I'm getting about 22 microhenries rounded about, okay? Now the common mode choke is right here. There's two windings on it, so let's go up to that. And I'm getting about 2.4 millihenries. So what we're going to do, we'll write 22 microhenries here and 2.4 millihenry here. All right. Okay, now here, let me show you the LCR meter. That's a nice matrix LCR meter, right? Okay, can you see that? I'm going to go ahead and touch the probes down so you can watch it in action. And all right, here's the differential mode. It's about pretty close to 22 microhenries, right? It's in circuit, like I said, so it's going to jump around a little bit. Now here's the common mode choke. All right, there's common mode choke, about pretty close to 2.4 millihenries. Now these are some differential mode chokes that it's kind of hard to read that part number on the bag. I'm sorry, these are common mode chokes, but there's the part number, if you can read that. Is written by some guy at Ferox Cube who sent these to me, and it's really nice that he sent these to me. But it's a 2P-80 or 2P80. I'm going to show you the data sheet on these in a minute, okay? But first, what I want to do is show you how we're going to do this. Here's our core. And here's our wire. It's insulated, and you can use any wire. If you're doing something, you know, for a certain design, obviously you need a wire that will carry the current. Now, if it's too stiff to wrap, you can use two smaller gauges that are equivalent and they're easier to wrap. It's called 2 in hand. You hold 2 of those small gauge wires, or even 3 gauge, you know, 3 wires with equal gauge, and you can use that. Okay. Now, guys, you might be able to get a hold of some kits for EMI designing, and this one might not be the right one, but it looks something like this though. And you get these cores, and they would have some information about them, like in the lid, like right up there. And if it was really meant for a common mode choke, you'd see these curves, impedance curves and stuff, which I'm going to show you. But anyway, the kit might look something like this, and you can pick out some cores and try to wind them. Okay. In this case, I ordered some cores from Ferrox Cube. They're nice enough to send me some samples, and we can use those to wind a common mode choke. Alright guys, we're going to have to strip this wire. And you know what? I think I'm going to cut it in two to start with, okay? Just fold it. And really like these, by the way. I'll put a link down below. These are super nice automatic strippers. So they have the little cutting blade up here, and then you can come down here and you can size this thing. I just kind of pull it back so I can eyeball it, and I just want to strip it about that much, I guess. Okay, super easy, super fast. And what's nice about it, I don't see it nicking or stripping off wires. It just grabs just enough of the rubber or the insulation, and I don't see it pulling away little strands of wire, even when I do fine wires. So I really like that. Now guys, what I want to show you is bring both wires in, okay? Same way. But we'll do one at a time, okay? But what I'm going to do is bring it in, okay? And if you imagine, I'm winding it around clockwise, okay? Doesn't matter. You can go either way. It's just as long as you pay attention, okay, to which way you're doing it. And I'm going to put, that's 3 turns. See, there's 3 wires going through the course. That's 3 turns. I'm going to do 4. It looks like I'm got enough wire to do 4 turns. And then we're going to measure it. So we're going to just pretend we don't know, because right now we don't know what the permeability of this core is. And the permeability gives you the ability to calculate what your inductance is going to be. Okay, so now this wire, I want to go through the same way and start winding it the same way I did the other one. Well, backwards actually, right? So I'm going to pull this wire so it's about equivalent to that one. Then I'm going to go around this way. Maybe I should have stripped them after I wound it, right? And you know what? Yeah, when you do a core, you want the wires nice and tight, but if they're not tight, you just get a little bit more leakage current. But now, see, if I look at each coil by itself, I got 4 turns on this one. And if I look down this one, I've got 4 turns on that one. Okay? So there's our 2 wires coming out. And here's our 2 wires coming in. So it looks pretty, it becomes kind of obvious that they're wound in opposite directions, right? So when the current comes in this way, it builds a field this way, okay? And then when it goes in this one, common mode, the same signal comes in this one, goes the opposite direction. So they're canceling the field on the core. So if it's common mode noise coming in this way, the 2 fields cancel. That's what we want, okay? Alright, so let's just see how the current flows through this thing, okay? See if we did it right. So as the current comes in here, let's say the line current's coming in here, running through the circuit and coming back this way. So as it comes in, it's going clockwise around the core. Okay, it comes out, goes out to our circuit, comes back, hits this one, and now look, it's going counterclockwise. So clockwise here, counterclockwise there, the fields cancel. So differential current that flows through our circuit, that circulates our circuit, cancels. And that's what we want. But if it's common mode, and if we have a signal coming this way, it goes clockwise. And if we go in this way, it looks like it's counterclockwise this way, but it's this direction. If we go around the core, that current is going clockwise, the same as this current. So those fields build really big and they cancel. Okay, let's measure it. All right, and measure one side of it. And wow, okay, I got about 2 microhenries. All right, then let's go on this one. And we have about 2 microhenries. All right, guys, that wasn't as much inductance as I was hoping for. So I recognize the 3E12, and that's a 36 millimeter core. And I recognize that 12 as being the high permeability. This other one's not quite as high. So I went ahead and wrapped the, well, let me see. I actually have 5 turns on this one, but here, let's measure this. Now the size of core isn't really why I'll get more inductance. Yeah, now I'm at 513 microhenries, so that's great. That's what I want, higher inductance. It's the permeability of the cores, the type of material, and then the size will help you carry more current, okay, without it saturating. But let's go ahead and wind the other wire. All right, guys, I went ahead and wound 5 turns on the other side. So, yeah, I mean, I could put some tape to keep it tighter, but even this way, watch what happens. I have to tell you what the meter's saying, but if I take this other coil, okay, if I take that coil, and if they're linked really well together, and I short this one, then it should short out the coil, right? And what I get is about 4 microhenries. So I get 500 now, a little over, but say 522, and then when I short this, I get like, you know, it's going to drop down to about 8 microhenries. So the reason it doesn't completely short out the core is because of the leakage inductance. Well, one thing you can tell, I don't have them wound tight, so they're not coupled as good as they could be, but they're never going to be coupled perfectly. So that leakage inductance is actually your differential inductance, okay? So I'm down around 3.4. I've put it a little bit tighter, and I'm about, when I short them, I get about 3.4 microhenries. So there we go. And now if I take this one, connect it over to the other core, so the current's going in this way and out that way. That's a differential current, right? And then I'll just short these, and I'm at 2.4 millihenries. So that's the common mode direction, and that's like 10 turns. So the way you calculate inductance is it's turns squared. So you get like 4 times the inductance when you put them in series. So 2.4 millihenries, okay? Now if I go to the other side of this coil on this side, and I take these 2, now I'm back at 2 microhenries. So now this field's canceling with that field, okay? And that's the differential mode. So I think I might have called the other one differential. The other one is common mode. They're in series. And when you're connecting in, you know, where the current goes through the circuit, out the other circuit like it is now, okay? So the current comes this way, goes through the circuit, comes back this way. That's differential. We're about 2.4 microhenries. So it's about the same as when I shorted it, right? And it should be. All right, I give you a view of the meter up there. Okay, now this is when I connect them together in common mode. See, it's about 2 microhenries, okay? Now if I move that and put them in series like I did before where it's common mode, I get 2.4 millihenries. Now if I just look at one side, so one side is about 500 microhenries, right? Now I'm going to short out the other side, and we're back to about about 3 point, shoot. Okay, I'll short out the other side, we're about 3 microhenries. So if I wrapped it tighter, we'd get a little bit better coupling and better example probably. Alright guys, so this is the Ferrox Cube spec sheet for that toroid. Its measurements are 36, 23, 15. And you can see, now, I'll cover this information in another video where we go deeper in how you choose the size of toroid. Right now I'm just going to show you how we calculate the inductance. But this VE, effective volume, that's the effective size of the toroid, and that's very important on how much energy it can handle. So that'll come up later, but for now, right now, this is the one we have, 36, 23, 15, the 3E12 material. And when you look at this column right here, this is nanohenries per turn squared. So you multiply this by turn squared, which cancels out this bottom one and gives you the inductance, okay? So when you look down this list, this material that I chose, 3E12, has the highest number, highest permeability. This is the permeability, like how inductive the material can be per every turn, okay? So you go 16,200 nanohenries, and then we multiply that by the turn squared, okay? And that's what we're going to do. Alright guys, I just wanted to go over some of these calculations that I talked about before. The X is C, 1 over 2 pi, F is 60 hertz, C is 2 times the 4700 picofarad. It comes out this 1 over 3.54 micros, and that is 282 k ohms. That's the X is C. Okay, so 120 volts over that X of C is 425 microamps, just about a half milliamp, which is the limit for the UL. Okay, that's why that's such a common value, the 4700 picofarad. Now that core we used was a TX36 2315 3E12, had that 16,200 nanohenries per turn squared. And the turns are 5 turns per side, right? So 5 squared times that is 405 microhenries. Now, if we put them in series like they would be in a common mode, it's actually comes out to 4 times that, right? So it'd be 10 turns. 10 times, 10 squared is 100. So instead of 25, it's 100. So it's 4 times more. Okay? Hey guys, I hope you liked that. Hope it made sense. Hope it's helpful for someone. And let me know. Give me your comments down below. I'd like to also do another video where I show how to determine the size, the volume of the core that you need so that you don't saturate it. And hey, by the way, alright guys, this core right here on the board is totally different from the toroid, right? And I meant to explain that. When you have a core like that and you have the slots, the windings are in separate slots, so obviously they're not coupled real close to each other. That's done on purpose. That is done so that you don't have perfect coupling, so you do have some leakage inductance, and that leakage inductance is differential inductance. So when you have your common mode choke, you also have some differential mode inductance, a little bit more, so that it works with the X caps and the common mode works with the Y caps. So with the toroid, you can loosely wind them. You can, if you have enough turns, you can actually leave one turn off one side, and that'll imbalance it and give that differential inductance. There's some danger though. You have to be careful that you don't have enough differential inductance to saturate the core, because they are such high permeability cores. They, fill up with the magnetic field very easily, right? And so that can saturate them if you have too much differential inductance. So you got to be careful of that too. So this kind of core and this kind of winding structure that you saw on the board, those are specifically meant to give you a little bit more differential inductance. Yeah, that's the way it is. And they're actually cheaper to wind, because you can wind those bobbins on the machine and then slide it over the core, versus a toroid that needs kind of a bobbin. It's a little bit different wind. You can kind of see how that would be a little bit more difficult, right? Has a little bobbin carrier that winds it, and yeah, a little bit different. But there you go, guys. Hope that was helpful, and I really like this matrix LCR meter. Works great, so it gives me confidence in the measurements. I'm going to compare some of my other LCR meters to that meter to see how they stack up. And also, when I look at multimeters and review them, I'll be able to use the capacitance on this to see how well the capacitance measurements stack up to the matrix. So, alright guys, hope you liked it. 2 thumbs up, my patrons as always, and I want to appreciate the guys that hit the thank you button down below, the one-time donation thing, buy me a cup of coffee, that kind of thing. And gosh, yeah, thanks for watching. A free way to support the channel is to subscribe and hit the like button down there, that thumbs up button. So, free way to support the channel. Thanks for watching, guys. Hey, we'll see you next time.